Right. Today we would like to finish the ADC design with with noise shaping. Actually, we talked about that oversampling can help us to increase the ENOB, but it is not so efficient. Okay. And then, what is the most efficient way to increase the effective number of bits? Actually, noise shaping is the best. All right. But noise shaping actually, the theory actually comes from some kind of predictive modulation. We call it delta modulation, and then we have delta pulse coding modulation, blah blah blah. Actually, delta means what? Delta means the difference between two samples, the closest samples. Yeah. We would like to code the magnitude. In the past, for ADC, actually, we coded the whole magnitude. All right, and you can think that is some kind of information wasting. Yeah, 浪费讯息. Why? Because if you would like to code the whole magnitude, it means the quantization level needs to spread all over the maximum to the minimum. However, if we only code the difference, the so-called delta, then you can see with the same number of bits, we can get very, very small quantization level. Okay, so that is the idea for delta. And we can go for such kind of noise shaping, yeah, sigma delta modulation, blah blah blah. But anyway, here now, this is almost the only structure we use to increase the ENOB. Okay. So, what is sigma delta modulation? With such kind of modulator, you can achieve the highest accuracy, but almost the lowest frequency. Why? Because it still needs to apply oversampling. Yeah, we don't apply this by itself, no. It goes along with oversampling. Okay. And how much oversampling? Very high. Yeah. Usually more than 64 all the way to 256. Yeah, you can see again 2 to some power. Okay, some power of 2, blah blah blah. Yeah, but what is the definition for noise shaping? Briefly, according to the past, if this is the spectrum, yeah, this is the baseband. I mean, that is the signal band. For voice, we have only 20 kilohertz. Okay. No, not the voice. For our audio signal. For our own voice, human voice actually 4 kilohertz, good enough. Okay, positive, negative, good enough. And how about the noise? I mean quantization noise, blah, blah, a lot of them. Okay, but right now we focus very much on quantization noise. Yeah. Okay, so after ADC, or before ADC anyway, okay, we have some kind of low pass filter, right? To cut off all those noise we cannot handle for our ADC. Yeah, I told you already. And then what is the power of oversampling? For oversampling, it can reduce the magnitude. Okay, but again, it is not it is not efficient. Anyway, according to signal to noise ratio, yeah, we can reduce the quantization noise. According to oversampling, it is really good because for in-band signal to noise ratio, in-band means in signal band. Okay, in-band, out of your signal band. So that is one way, yeah, to reduce the noise. And then you can increase. How about the signal? The same. The signal power is still the same, but anyway, we can reduce the noise power. So S over N, signal to noise ratio will be increased. Then we can increase our ENOB again. Yeah, but what is noise shaping? For noise shaping, actually, the concept is totally different. The overall noise energy, especially quantization noise energy, is still the same, but we try to reshape it. Okay, reshape. It means the noise spectrum is not the same as before. After you apply such kind of delta sigma modulation, but after that, what will it look like? Okay, because the total noise energy is still the same, but we try to move the in-band noise to be out of band. That's it. Okay, so if I replot this one for you, this is a signal band. That is the original noise band. We try to not lower down overall noise energy, no, but we try to make it look like that. Okay, this is again positive and negative spectrum. Then you can see, oh, you get higher noise energy at high frequency band, right? And how about the in-band noise? It is reduced. Again, I need to tell you, the in-band and the out-band noise, overall the energy should be exactly the same. But we try to modify the shape. Okay? In the past, quantization noise, every kind of noise, it is supposed to be a white one, a white noise. What is the definition for white noise? I told you already. From DC all the way to very high frequency, the noise is uniformly distributed. It means the magnitude from very low to very high frequency band seems about the same. Okay, but right now it has such kind of shape. Okay, yeah. So even though we don't reduce the overall noise power, but again, we need to apply some kind of low pass filtering, right? I told you already, for all those frequencies we cannot handle, you need to move it, you need to filter it. So you can see in band, the noise magnitude is substantially reduced. And again, enough will be substantially increased. That is what we want for such kind of noise shaping. Yeah, to move out the in-band noise. Yeah, to high frequency band and filter all of them. That is what we need. But why and how? Yeah, this is some kind of block diagram, but allow me to explain. Yeah, noise shaping. Yeah, from regular noise ADC to oversampling, you can see the magnitude is reduced. The noise power is reduced uniformly again, but it is inefficient. Okay, then let's go for the idea for delta sigma modulation. Yeah, why we can achieve something like that? Actually, we copy and paste. Actually, we duplicate such kind of idea from communication. Yeah, our linear system. In the past, I think you guys already learned something from communication system or from linear system, blah, blah, blah. Yeah, that is the so-called delta modulation. Yeah, as I told you already, PCM pulse-coded modulation. It means, again, yeah, we quantize the overall magnitude. Then go for delta PCM, delta pulse-coded modulation. We only code the difference instead of the magnitude itself. Okay, your magnitude, the difference between you and your senior. Yeah, your senior is such high, such tall, then you are taller or shorter than him, right? We only code the difference. Yeah, that's it. So it means what? The number of bits per code can be reduced very much. Yeah, that's it. That is the very easy to understand concept. If, again, such kind of idea needs to be applied with oversampling, I told you already. So if the sampling frequency is increased very much, what does it mean? Okay, yeah. Very interesting. Okay, for example, if this is your input, anyway, in the past, wow, from here, yeah, from maximum to minimum, right. And now we only coded the difference. The difference, how many bits you need to code the difference? It depends on how high the sampling frequency is. If we increase the sampling frequency very much, this is mine, that is you, right? This is mine, that is you. Because increase the sampling frequency, it means that the difference between two samples will be reduced correspondingly, right? So in theory, if you increase the sampling frequency very much, that is the idea for oversampling, then 1 bit should be good enough, should be sufficient. But why? Because we are very close, so I only need to know, I'm higher or lower than you. That's it. Okay, if I zoom in this for you, wow, okay, I'm here, you are there, right? So for the next, it is smaller than me. That's it. But if I zoom in here, I'm here, you are there, then you are higher than me. That's it. 1 bit should be good enough. Okay, but maybe you are still curious. Okay, let's go further, just like this. See? Because this is the block diagram. This is the block diagram for filter modulation, filter modulator. Okay, and we need to have some kind of demodulator later. This is modulation and then demodulation. From analog to digital, and then go back from digital to analog. And then we need to get exactly the same thing in theory. All right? Yeah, let's go for it. That is the input signal, and that is your coded output signal. Okay, so why you need to? Because we would like to get the difference. I'm here, and what is my previous one? This is the previous one. So it means what? You need to reconstruct your previous sample. Okay, through what? Through integration or summation. Okay, I told you already. Integration for very small period means summation. Okay, so the idea is here. That is the current input, and that is the previous sample. We take the difference. Got it? We take the difference. So if the previous here and the current is here, right? We only take the difference. See? Summation, positive, negative. We take the difference. And then this is the 1-bit quantizer. To see, hey, I am larger or smaller than my previous sample. For example, I am larger here, you are smaller, right? So we get 1. But how to reconstruct it? 1 means positive, right? Positive means what? That is the previous one, this is the current one. Next sample is higher. So how to reconstruct it? This is also some kind of very small increment, summation. So this is this is the previous one, and how to achieve, how to reconstruct the current one? We just step up. Okay, so here we increase 1 step. What step? 1 quantization step. Got it? 1 quantization step. Maybe you will say, hey, if I zoom it in again for you, There's the previous one, that is current one. Oh, positive. The current is higher than the previous one. We need to increase the previous one one step. So one step maybe here. It's still not enough, right? One step maybe there. Oh, too much. Okay. I don't care. I don't care. All right, because, yeah, so I'm less, the current one should be increased, right? Become your representative previous sample and then compare with the next. Okay, so if something, maybe you will be curious, hey, if I increase very much, just like this, so that is the current one, and then, right? Oh, you cannot catch up with this, right? This is the input. Yeah. So how to make it increase the sampling rate? Yeah. If you cannot catch up with that, because that is the previous sample, and this is the current sample, then, for example, we double the sampling frequency. So what is the next sample? Here, in between, in the middle, right? In the middle, you can see, hey, if I increase it even only one step, I will be higher than the ideal value. Okay, I mean the reconstructed one. Okay, got it? So, if again you increase the sampling frequency very high, then 1 bit to increase it or to decrease it, good enough. Yeah, to reconstruct the previous sample, good enough. That's it. Okay. So, yeah, this is what I would like to tell you. For example, if your input is increasing, then you will get a lot of step up. It means that you get a lot of one, because you need to trace your increasing input. You need to step up. However, if like this, you need to do what? Step down, right? That's it. So here you will get a lot of ones, and there you will get a lot of zeros. Got it? Got it? And how about the flat region? 平滑的. It means the slope is around 0. Okay, if I zoom it, woo, okay, so you mean I'm here, next. So you say, hey, I'm here, so I need to increase. Oh, too much. I need to decrease. Oh, too small. So what do you will have? 1 and 0, right? Right? Got it? So with such kind of concept, even you read the output, you will know, oh, if you got a lot of ones, it means the input slope is increasing. If you got a lot of zeros, it is decreasing, right? If you got a lot of 1 and 0, 1 and 0, 0 and 1, 0, oh, yeah, you can guess the input slope is really small. Got it? That is the idea for Tilda modulation, and I explained already. If the input the sampling frequency is high enough, then 1 bit. Okay, good enough. More than good enough. Okay, wow, only 1 bit. It's fantastic. All right, but you will see, hey, how to do such kind of demodulation? Oh, piece of cake, because the demodulation is already embedded here, because we need to reconstruct the previous signal. Got it? Got it? So, how to go back to the analog signal, the original analog signal? You simply sum all them up. 1, 1, 1, 1. Oh, it is increasing. 0, 0. Oh, it's decreasing. That's it. Okay? Yeah. So you sum them up. But even though you sum them, I mean, this and that are exactly the same in idea. Okay? So you already embed such kind of signal reconstruction in the modulation structure. But for reconstruction, we still need to duplicate this idea. Okay? Yeah, the concept, the structure need to be duplicated here. But even after reconstruction, you will get such kind. So what you need to do? Low pass filter. That's it. Then you will go back. You will get back the original analog input. That's it. Piece of cake. However, we would like to do more. Yeah. This is the original structure for delta sigma. Delta sigma, sigma delta. I don't care because people sometimes speak in this way, sometimes speak in that way. They are exactly the same. You see, modulation and demodulation. This is the modulator, 调变器, and this is the demodulator, 解调变器. And this is the reason why we try to borrow, duplicate the same idea from communication system. Actually, for you guys, maybe the first time you learn such kind of delta modulation, I guess, from communication system. Okay? Yeah. So you can see, what is innovation? Sometimes you don't need to create the brand new idea. No. You can apply one idea in this field, then into the other field. Then you still create some fantastic results for humankind. This is a very good example. Humankind knew such kind of delta modulation maybe more than 100 years ago, hundreds of years ago. But they never thought to apply the same concept to analog IC design. But sometimes somebody did some good things. Yeah, he or she thought about this. Oh, why can't we apply the same concept from communication system to ADC? Oh, bingo, we make it. That is the most accurate ADC structure till now. Okay. Anyway, that is the original one, but we would try to simplify it. So that is original modulator, demodulator, blah blah blah. In the past, for such kind of, for example, MP3. Yeah, the concept is quite similar to this. For the audio, you have many kind of. If you read the content of a CD-ROM, okay, for some kind of music, yeah, overall 60, around a little bit more than 60 minutes, okay, and how large it is, usually more than megabytes or something, I forgot, okay. Anyway, if you recode it through such kind of concept, yeah, the overall size can be reduced maybe 4 to 5 times, okay. But if you can tolerate more distortion, then yeah, maybe only 1/10. Okay, it means one CD-ROM in the past maybe the most is 20 songs. It depends on how good the artist is. Yeah, if he or she is good-hearted, maybe 20 songs. If he or she is so bad, maybe only 10 songs. Yeah, you still pay the same amount of money. I mean, in the past. Anyway, by such kind of delta modulation on each CD-ROM, we can increase the number from tens to hundreds. Exactly. So if you get in car, for modern cars, they have any kind of MP3 player in the car. So one CD-ROM, hundreds of songs. Yeah, you can enjoy from Taipei all the way to Kaohsiung. You cannot finish all of them. Okay, in the past, you need to maybe when you drive before Taichung, you finish all of them. You need to replay, right? But right now you can drive all the way. Yeah, maybe even to Hong Kong. You don't need to change your CD-ROM. Anyway, in the past, for such kind of modulation, for one CD-ROM, to my experience, it takes hours to do such kind of modulation. But right now, we can do the so-called real-time modulation. Okay? Real-time means what? If the song, even the rate is higher than real-time. Okay? According to hardware acceleration and the evolution of your CPU, GPU, anything. Okay? In the past, one song maybe takes, I cannot say 1 hour, but maybe more than 10 minutes. Right now, less than 1 minute or even seconds, you can get the result. Congratulations. What I would like to tell you is, for this one, it takes a long time. And how about the demodulator? The same. Yeah. So you cannot listen to the result, right, in a real-time style. You need to wait for decompression, demodulation. After that, you can listen to the audio. It doesn't make any sense. So in the past, the speed of your hardware is too slow. So we try to do some help. So what we can do is, yeah, see, we move this one from modulation to, from demodulation to modulation. Okay? Why? Oh, according to linear system, yeah, from the input to output, you have A and B and C. Then you get output. So what is the equation for your output? Oh, you will say, hey, O means A and B and C by the input. That's it. So if you change the order, the sequence of ABC to become BCA, ACB, who cares? You still get the same output, right? That is what we learned from the past. So never mind, you move what block from input to out, from modulator to demodulator, or from demodulator to modulator. Who cares? So yeah, you can make it here. Okay, but why? Because after moving the most expensive part from your demodulator to your modulator, then the cost for your demodulator will be substantially reduced. And it means everybody can enjoy the music very, very easily. But you can say, hey, it complicates the structure of your modulator, right? Your quantizer, right? No worries. We are intelligent humankind. We can do something even better. Okay? Yeah. The other theory is summation means integration. Anyway, okay, I don't care, summation or integration. Okay? You can see you learned already from calculus. Right? The summation of input and the summation of your digital output, then take the difference. That is this idea. But we can make it like that. You take the difference first and do integration or summation. Right? The same. Right? Okay. Yo. And this is the final structure. See? You still have summer integrator and one bit quantizer. 1, 2, 3. See? Exactly. I mean, the hardware is the same. It's totally the same. But we reorder them. We change the order of them. That's it. So from the first step, we move it here. Oh, it has two integrators, right? But after we move the integrators to the, from the input to the output of the summer, we simplify the modulator again. Oh, congratulations. It means what? The complexity of your modulator is still the same as the original version, but we reduce the complexity of your modulator very, very much than before. So that is the current structure. Okay? If you are happy with about the theoretical study, then yeah, we can do Laplace transform to get the transfer curve, the transfer equation from input to output, blah, blah, blah. Okay, so for Laplace transform, what is integration? Integration means this. Okay, differentiation means S. T 微分得到 S， 积分得到 e 除以 S。Okay, that's it. So allow me to show you such kind of simulation. For simulation, yeah. Oh, yeah, because you have such kind of. Later, I will show you the derivations. Okay, yeah. After you transform from time domain according Laplace transform, Laplace 转换 from time domain to S domain. Okay, we get this. Oh, you can analyze the relationship between your input and output, blah, blah, blah. Okay, later I will show you. But before that, I show you the result, the simulation. Okay, in time domain, wow, this is in original time domain. We have sine wave as the input, okay, and the blue one, V, as the output, the distal output stream, bit stream. Yeah, you will see, hey, where are the, I told you already, if you got a lot of ones here, I think this is a lot of ones, more ones here, okay, more zeros there. Yeah, you can see empty to the top. So it means most of the bits actually are to the bottom, okay? And in between, 1 and 0, 1 and 0, 1 and 0, 1 and 0, right? That's it, okay? Got it? Is it correct? The simulation needs to match the theory. Okay, so right now, what you see is a lot of 1, 0, 1, 0 here and there, right? And then a lot of ones here, a lot of zeros there. Is it correct? Is it correct? No. Why? I told you already. Here, you will get a lot of ones. There, a lot of zeros. To the top and the bottom, the slope is around 0, right? So you will get a lot of 1, 0, 1, 0, 1, 0, or 0, 1, 0, 1, 0, 1, 0, 1. Okay? So you see the simulation result is 90 degrees shifted. Why? See? To the positive slope here, you need to get a lot of 1, 1, 1, 1, 1. Okay, a lot of 1, 1, 1, 1, 1. And here, a lot of 0, 0, 0. Right? And this is the reason why I told you, wow, 90 degrees in shift. Is it correct? Yes. But why? Okay, let's go back here. The logic thinking I explained to you is according to the original structure. But for the final structure, actually, we move this to there, right? Here, right? Integration means what? Sine will become cosine, cosine will become sine. Got it? So the 90 degrees in phase shift actually is caused by such kind of multiplication. You shift integrator from demodulator to modulator, and it caused this one, 90 degrees in shift. Okay, that's it. So it's still accurate. It's still correct. Don't be fooled by the time domain simulation. It's totally perfect. Okay, but you need to know the reasons why. Right here. Okay. All right, and then we go for, this is not so interesting. So let's go for the spectrum simulation. Wow, wow, what? This is the frequency of your sine wave of your U here, a nice spectrum. But how about the quantization noise? This is what I told you already. Without such kind of noise shaping, it should be flat. But right now, it looks like that. Very low in band, very high out band. So you only need a low pass filtering to cut all such kind of high frequency noise, quantization noise. Congratulations. The in-band signal to noise ratio will because the noise in band is substantially decreased. So you will substantially increase the signal to noise ratio effectively. Your effective number of bits will also be substantially increased. How simple. That is the simple idea for you. So you can see the power of knowledge, right? You learn something in communication system, then apply the same concept to ADC. Wow, you achieve the most accurate ADC till now. Okay, you don't need to learn different or new things. No, you duplicate your old things to make new achievement, very good achievement. So this is some kind of, I had better swap it. Yeah, this is some kind of analysis. How to analyze it? I show you this. Piece of cake, right? You have, yeah, the input, the output, and according to quantization, you have what? Quantization error, or the so-called quantization noise. Okay, and quantizer is not perfect. Yeah. Oh, too much. That is the error. Or one step. Oh, too small. That is the error here. Got it? Okay. So, with such kind of easy to test structure, you can analyze the relationship between your output and your input. That is the most important one. Oh, no. The most important one is the output and your noise. Okay? So can you do the analysis here? Piece of cake, right? Very easy. Within 1 or 2 minutes, you can make it. Okay, wow. And then you get this. Signal transfer function. Yeah. Y is the output. X is the input. So Y divided by X, you get this one. What's that? In S domain, that is low pass filter. Okay, the first order low pass filter. That is what I told you, easy to test. Okay, only the first order low pass filter, so the spectrum look like this. So what does it mean? Oh, all right, I need to tell you, the cutoff frequency is normalized. Okay, normalized, 正规化. Yeah, for the real one, it depends on your device value, your equivalent R, your equivalent C, your equivalent what. I don't care. Okay, yeah. Anyway, it means if the input frequency is not so high, in this region you can see the magnitude is 1. For DC or for very low frequency. What does it mean? Your output will be almost equivalent to your input. That is what we want. Okay, never mind, because for any kind of conversion, we hope the input and output are exactly the same. Got it? That is in theory. And right now I show you, because in this region, the magnitude of such kind of transfer function is 1. It means output equals input. Perfect. But out of that, sorry for that, no. Okay? And that is, for your real design, yeah, you need to know how much is the real bandwidth. Okay? Yeah. Without any normalization. Okay, let's go for the next. Noise transfer function. We get that. What is that? First order high pass filter. Okay? If you are curious, please go back to read your fundamental circuit theory. Yeah, because that is the most simplest one for what you learned from your fundamental circuit theory. 你若怀疑 登一堂的基本电路学，一开始就讲。Anyhow, yeah. So this is not good. It looks like that. Okay. It means what? For in-band, what is in-band? Again, your signal band, you just cut it here to there. You can see for in-band, oh, the condensation noise becomes so small, but out-band it becomes so large. But that is what we want because we need some kind of low-pass filtering, right, before ADC, so we can cut it. Congratulations. Okay, yeah. So you can see, in brief, the signal transfer function looks like a low-pass filter. Yeah, in theory, we hope we can get this. 1 in band, 0 out band. Okay, how to achieve that? In theory, you need to increase the order. If you increase the order of such kind of signal transfer function from first order to second to third, congratulations. Yeah, the transition band will become steeper. For the first, second, third, first, and finally, in theory, you can achieve this. Okay? Wow! In band, 100% passed. Out of band, 0% passed. Okay, that is what we want. And then how about the noise transfer function? The same. If you increase the order, right, from the first to the second to the third, again, the transition slope will become steeper and steeper and steeper. Oh, that is what we want. So in theory, with infinite order, it will look like that. Zero noise in band, yeah, and all the noise energy is moved out. Well, what does it mean? This is almost 0. So you have infinite number, equivalent number of bits. The ENAB will become infinite. Wow. Okay, but that is only in theory. How about in practice? I need to tell you, first order, good, but the performance is not so good. Okay, then second order, wow, it's also good. Yeah, the performance is improved. And how about third order? If you would like to improve such kind of transition, okay, third order, yeah, it is possible, but you need to be very careful because for third order delta modulation, it is more likely to be unstable. Okay, so only if you are really experienced. Otherwise, don't try third order modulation first. No, from the beginning, I guess the most is second order for you. Okay, for your first design, second order, good enough. Otherwise, if you design something according to third order, yeah, you will get some kind of ridiculous result. Oscillation. Even you have PC for your ADC as the input, right? And the output after reconstruction will look like that. Oscillation. It doesn't make any sense. All right? So, yeah, theory is theory. Practice is practice. 现实就是这样子. So, I hope from the beginning you focus on second order delta sigma sigma delta design. Okay, that is the block diagram of the first order. Yeah, I told you already. And then that is spectrum. It is not so good. The first, okay, maybe this one. Yeah, the first, the second, the third. As I mentioned, the higher order, the better, because you move more and more in-band noise to be out of band. Okay? But I need to warn you again, for third order sigma delta modulation, it is more likely to be unstable. Yeah, stable, maybe unstable, so you need to be very experienced. Otherwise, something will go wrong after fabrication. Anyway, for digital signal processing, that is the so-called DSP. Yeah, we don't have Laplace transform. We have Z transform. Yeah, but anyway, I have no time to explain that. But I would like to tell you that, yeah, even you do such kind of analysis with DSP, I mean with Z transform, you still get the same thing. Okay, means what? Signal transfer function is low pass, noise transfer function is high pass, something like this. Okay, and the higher order, the better. That's it. Yeah, you can see. That is for the first order, and then, yeah, the second order. You can see. Even less in band. Yeah, just again use your eyes as a camera, right? Then if you go back, you can see how much in band noise for the first order. That is first order, okay? And this is the second order. Substantially reduced. You can enhance the SNR, signal to noise ratio, and then enough. Okay, very good. So, equivalently, this is the OSR means what? Oversampling ratio. Because according to Nyquist rate, right? Your your sampling frequency should be 2 times higher than your highest input frequency. Okay, and beyond that, we call it oversampling. But how much in ratio? For example, for our voice, for our audio, I told you, for human ears, 20K. So sampling frequency needs to be 40K at least. All right. If OSR is 2, it means you get the Nyquist rate by OSR will become the real sampling frequency. That is because this is only the ratio. Okay, that's it. Yeah, and so 2 times higher, not enough. 4, 8, 16, not enough. For such kind of sigma delta sigma modulation, yeah, ADC, as I told you, at least 64 and all the way, yeah, to 256. Okay, so this is a briefly review of the power for delta modulation. Okay, you can see, this is OSR, oversampling ratio, as I told you. For real design, at least 64, all the way to 128, 256, blah, blah, blah. And this is the number of bits for your quantizer. 1 bit, 2 bits, 3 bits. Okay, and how about L? The order of your delta modulation. The first order, the second order, and the third order. Okay, yeah, I told you it is possible, but very hard for new designers. Let's see the effective number of bits after such kind of modulation. Yeah, you can see even with only 64 oversampling ratio, 1 bit quantizer, and third order. Wow, we make the effective number of bits for about 18 bits. 18 bits! For regular ADC, forget about it, because I told you already, even for experienced IC designers, analog IC designers, it's really hard to achieve anything. I mean the enough close to 12 bits. Very, very difficult. But right now, piece of cake. Only 1 bit quantizer means above or below. That's it, right? Wow, ridiculous. Yeah, but you need to design the third order. Okay, if we move further, if increase the oversampling rate 2 times more, from 64 to 128. Wow! Here, again, even with only 1 bit quantizer and third order modulation, wow, we get more than 20. So this is the reason why for oversampling, for noise shaping ADC, for experienced designers, if they cannot achieve the ENAB better than 20, I guess they will be fired by the company. Okay? 20 bits for ENAB is some kind of regular requirement for designers in this field. So if you would like to enter such kind of, sigma delta ADC, please train yourself to be experienced enough to design ENAB, to achieve ENAB better than 20. Okay? Yeah. Anyway, there's another comment about the number of bits for your quantizer. 1 bit means perfect. Okay, why? Okay, let's check. 2 bits. 2 bits means what? You need 1 and 2 and 3, 4, right? You need to make sure they are perfect. Okay? What is perfect? The effective accuracy should be more than what you would like to achieve. Got it? At least 2 bits to play safe. So if you would like to design this, right, it means the effective accuracy should be around 20. But you may be curious, hey, I have only 2 bits here. How to achieve 20? I told you already. For example, according to INL, right? If you would like to make sure 2 bits are effective, then the error should be less than, right? How to make 1 bit quantizer or 2 bit on the 2 bit? The ENAB to be 3. The error needs to be this. To be 4. Okay? To be 5. For 1 extra bit in ENAB, you need to reduce the error, INR error, by 50%. That's it. So to make it as 20, you can guess how small the error you can tolerate. Okay? Is it possible? I can assure you, almost impossible. We are humankind, we are not gods. Okay? Got it? 如果你要把你的2位元的quantizer 做到里面，那你要非常小心哈。它能够容忍的误差非常的小。理论上，如果你只要2位元，它有1/2 LSB 的容错，变成3位元除以1半，变成4元再除以1半，变成 so you can see very 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 small tolerance for even this. Okay? Don't try. That is my recommendation. Don't try this. Don't try that, because your deck always has many kind of errors. It is not perfect. Imperfection. Okay? So what my recommendation is this. 1 bit. 1 bit is perfect. But why? Okay, for differential operation. Oh, that is some kind of tricky idea, okay? Anyway, the minimum, the maximum, you may say, hey, 1 bit means in the middle, right? In the middle. And again, you have a lot of problems. No. Why? That is only idea. Okay, in idea, in theory, it looks like that. In practice, I told you already, nobody will apply real-to-real input for your ADC unless they are full. Nobody. So it means the real input will be smaller than your maximum or minimum. The range will be reduced. So, congratulations. You don't need to worry about, is it correct? No. Only if for real application, you can see the real input will be reduced, right? That's it. Who cares? We don't care the real, we don't care the ideal maximum, we don't care the ideal minimum. No, we don't need to care about that. So the threshold to be positive or negative, up to you. I can say up to you, but you have much more flexibility. Okay? That's it. 你大家听有哈？实际的应用，你的输入范围一定会往内缩。所以顶管甲下骹无对称袂死人。你听有哈？ That is the easy to test idea, and this is the reason why one bit quantizer always means perfect, no error. Okay, and how about 2 or 3? Oh, forget about it. I have 2 or 3. Yeah, even though your real input is not real to real, but you still need to make sure this and that to be perfect. Okay, so from the beginning, my recommendation is 1 bit quantizer, and from second order. And you say, hey, too bad. Okay, you move here. Not so bad, right? 16 bits already. Okay? So after you get very good experience, then push for this. Third order. I told you already, it is not impossible, but very hard for new designers. So from the beginning, don't focus on this. Okay? To be humble, here, good enough. For your first design, after you achieve something with good enough performance, then move to the next step to make your enough better than 20. Okay. All right, that is what I can tell you. Yeah. How about the brother? Yeah. Okay. Because I don't have enough time, you can read it by yourself. From analog domain to time domain, not fully in time domain. Yeah. No. Okay. Briefly, I would like to tell you. With the help of time domain comparator, okay, we can reduce the overall power consumption very much. A very simple idea. Yeah, for ADC, never mind what kind of structure, you still need to compare your input to output, right? Even here, yeah. Your quantizer. See? You need to compare your reconstructed output to your input. Okay? So, if you compare such kind of input and output in voltage domain, you need voltage comparator, right? It is really power hungry. And also, you need to face VOS, voltage, input offset voltage. You cannot make it 0. No. Yeah, the best till now is around a few microvolts. But for such kind of design, the op-amp is really expensive. It occupies a lot of chip area, consumes a lot of power, blah, blah, blah. Are you happy? Usually not. For such kind of very good, very luxury comparator, I think that is only good for instrumentation. not for our daily life applications. So we need to reduce the cost, but still achieve good enough performance, right? That is one of the bottleneck for ADC design. Never mind what kind of ADC. How to reduce VOS, really hard, right? Okay, so we wouldn't like to do such kind of comparison in voltage domain. Yeah, somebody do something. This is the fourth idea. Yeah, you can see if you check the paper, okay, to be honest, with such kind of very slow sampling rate, and the ENAP looks not so good, but it's still published in ISCC. That is the top one IC design conference. Even harder to publish paper than top one IC design journal, say SSC. But why? Simply because it created the first concept, okay, to compare the input-output voltage, the input-output signals in time domain instead of voltage domain. But you may be curious because from the very beginning, the input is voltage. The reconstructed output is still voltage. How can they do it? Okay, here. Voltage to time. Okay, voltage to time converter. And then do time comparison. Okay, first of all, how to compare the signals in time? D flip-flop, good enough. Okay, I think I told you already. For D flip-flop, one is for example, your input, okay, and then your output. Okay, so I reversely explain the idea, the concept. If this is your input, okay, and then that is for data, right? So what is your output? If your output is here, delayed, we will sample 1. If your output arrived earlier, we will sample 0. Oh, piece of cake. The early or the later, right? That's it. With D flip-flop, we can compare the time. We can tell who arrives earlier, who arrives later. Okay, but you will be curious, hey, my input is voltage. Okay, for V to T, right? That is the input, and that is the output. VITI, VOTO, I don't care. Yeah, in theory, you have such kind of, in theory. Okay? So, the larger output, the larger input, the longer output. That's it. Okay? And then you will say, hey, how about the transfer curve? Does it need to be linear? To be honest, no. Okay? Why? Oh, that is the last help I can do for you. Yeah, according to time is much limited. Yeah. Oh, even more fantastic. Oh, it is not good, right? From input voltage to output time, if it is not linear, what's the consequence? No consequence. In theory. Why? Because if I'm here, I got this time. If I'm there, I got that time. Still good enough. Because right now, for your comparison, in voltage, it means higher or lower. In time, earlier or later, right? Right? So only if larger voltage get longer time, you can still tell the difference. That's it. 安尼听有吼？电压轴的比较，比关系，时间轴的比较，比长短，加较先来，加较后来，前后，对不？所以咱这个转换只要你大的电压 转换出长的时间，小的电压转换出短的时间。啊，你是要赶快逼出你的前后关系呀？啊，听有吼 ？Got it. Wow, wow. I really appreciate the innovation of the authors of the paper. Fantastic. They try to explain. Oh, sorry for that. They try to explain. You don't need to have perfect V to T. No. Even it looks like that, still good enough. Only if higher voltage, longer time. Smaller voltage, shorter time. Good enough for such kind of V to T conversion. Okay? You don't need to spend too much time on such kind of V to T. Wow. Fantastic. All right? And how about the D flip-flop? I told you already, yeah, you have the so-called metastability. If the input and output are very close to each other, then the output is not 1 or 0. It will cause some kind of trouble for you, metastability. Okay? But according to process evolution, the setup time, the hold time is decreased with better technologies. So it means what? The equivalent VOS in voltage domain, right now in time domain, we call it sampling window, I told you already. For such kind of sampling window, it can be reduced substantially through the help of new processes. You don't need to do anything. TSMC or UMC will help you. With better processes, you can effectively reduce the impact of the so-called VOS. Okay? Got it? Got it? So, finally, to conclude, ADC, this innovation is very important. To replace voltage comparator with time comparator, we substantially reduce the power. And also, the impact of input offset voltage. Because right now, in time domain, okay, the problem can be solved easily with new processes. That's it. You don't need to do anything. Okay? With two important innovations, even though the result is not so good, the paper was still accepted to publish it. To publish in ISSCC, that is really hard. Okay? Hopefully you learn something instead of nothing, yeah, through my explanation. And this is the end of ADC. So for the rest, I would like to introduce period design. At least I will show you from the theory all the way to simulation, or even if I have time, behavior simulation for phase lock loop. Why? Because that is the second important IP on Earth for analog IC designers. Okay, let's have a break right now.